a first introductory lecture following the line of our textbook, which is how the body shapes the way we think. You know that in the last lecture we will have a very interesting lecture by Rob Pfeiffer. We had actually one of the two co-authors, Josh Bongard, in the very first guest lecture. We will have Rolf Pfeiffer, the other author, the main author, in the last lecture, and this last lecture will be entitled How the Body Shapes the Way We Think 10 years later, because the book is now almost 10 years old. And then we will have a guest lecture today from Martin Sterlen of the University of Plymouth, who is one of the persons who have contributed to keeping alive the guest lecture for several years. I'm also proud to say that he is now a professor, but he is my former student in Madrid. And so, welcome everybody. So we can start with today's lectures. So the topic of today's lecture is emerging intelligence, cognition from interaction, development, and evolution. I would say that we have already touched in a very quick way those topics, no? Because basically the overall idea inspiring these lectures is that we should go for a paradigm change in the way we conceive and design robots. And not just robots, because also in nature we have those principles are working. In particular, it's very interesting the example that we introduced in one of the past lectures of a model of the way ants work, introduced by Holger Kruse, a German biologist. I underline by a biologist. This actually is an example of what we are looking for. So a kind of trade where we take inspiration from the principle of organization of existing animals or plants in nature, and we use them to model to build robots, and then we go back. This example of the ant, it's quite important in this point, because what we have seen is that despite what we may at first glance think, the ant isn't a central controller. You remember that we have shown that the picture of a traditional approach to control of robot, which is you have sensors, you have a perception, for example, a vision system abstracting object from the scene of the environment as it is seen by robot. A planning phase, so let's say that your robot needs to go from point A to point B. It looks how the environment is shaping and plan an optimal trajectory, avoiding the obstacles, and then act. So after you have a plan, so after you have perceived the scene, which means made a model of a scene, you have planned what you want to do, then you start to move the first foot and you go from A to B. The approach that we have seen, and we will come back on this today again because it's very important, proposed by Brooks in his famous paper on 1986, intelligence without representation, talks see the problem in a different way, a set of concurrent parallel processes. So very similar to what we have seen in the example of the Simon's ant on the beach. So it knows that let's go forward, and this is one of the concurrent processes. Another one is avoid obstacles, meaning that if you hit an obstacle, you move by a certain extent on the right, and then you start going again, so without knowing where the obstacles are on the terrain, on the beach. So it's interesting to see if we go to see a real ant, it works according to Brooks' model. So it has a connection between the neurons controlling one leg and the closest other leg of the ant without a central controller. So the mechanism is exactly what we would expect from our view. I would add that an ant is not completely, so it's not liquid, so it has a structure, so has a kind of stiffness. So the ant body has some stiffness, and also the legs have some stiffness. But if you look careful to any ant, you will notice that they are also particularly compliant. So in a simple example, like an ant, we have a kind of summary of the principles that and ants are quite, if compared to mobile robots that have been developed so far, are particularly good. Now we have this example from Fumiya Ida that was then at the AI lab in Zurich and is now a professor in Cambridge, of the puppy. The puppy is a quadruped where with a very simple control, where you have passive legs, you see in the picture, and connected by spring. The interesting thing is that this puppy is able to move in a very natural way on a treadmill with very limited control. So it's a kind of implementation of example of the hand. Where are the differences? Well, there are several differences because, again, what is actually driving the locomotion is the natural, so to speak, dynamic of a robot. There is an analogy of the fact that we have springs. So we have the rigid part of constituting the legs, if you look at the picture, and we have springs connecting them. If you choose carefully the structure of the legs and the stiffness of the strings, you can have a good motion with a very limited effort in writing a controller. So it is while one of the big pieces for those who have looked into it of a locomotive, of a robot walking, whether it is a humanoid or a quadruped or any other robot, is dedicated to stabilization. So calculating the center of mass and positioning the foot and the legs and the body attitude in a way that doesn't move the center of mass outside, so to speak, of the shadow of the system, Here, the stabilization is achieved naturally as an effort. So where is the difference with ant? But if you look at an ant, it's much more, all the body is soft, and you have more sensors. You also have more control, but not for controlling the stability. And another nice difference is that on a treadmill, you have a very simple terrain, no? Because it's basically like walking on a treadmill is like on an horizontal treadmill is like walking on a flat surface straight. In the case of the ant, the ant interact with the soil, with the terrain with the beach. So what I really like of this ant is that it works as we expect, so as Roomba, so to speak, because also Roomba, with as I repeat, but it's also worthwhile to do it, works more or less on the same principle, because it has a number of concurrent parallel processing following the dust and going back when it hits a wall or an obstacle. So it's again a simple, but in the case, the ant is also nice because it's those studies shows that also Herbert Simon was right, because a lot of information determining the actual path of the ant on the beach is given by stigmergy. Stigmergy is the word that we use for communication between parts of a system through the environment, because the legs are connected with the closest one, means that the communication between the right and the left of the ant is through the reaction forces on the terrain. So this is quite interesting. So I repeat this because it's one of the core concepts that we are carrying in this series of lectures. So the real, a deeply biomimetic structure for a robot, as it was, for example, was first described by Rolf Pfeiffer and some collaborators in Science, again 10 years ago, is this one. So you have a controller which has basic functions. For example, not determining the trajectory of my arm, which is to a large extent very similar to what happens in the ants and what happens in puppy. So it's determined by the structure of my muscle and my bones and my arm, which is partially deformed and so on. But the point is that it's the gravity which basically moves this. And what does my central nervous system does with respect to this movement? Controls the angles of the joints here and maybe here, but little more, which is quite different from calculating the trajectory in X, Y, Z, and then doing the inverse kinematics. So we don't need inverse kinematics. Well, no, it depends on what you want to do, but very likely in nature, natural animals don't perform inverse kinematics. They perform something that anyhow could be similar, because I have a kind of activity level, because I know that I want to go here, so my brain knows that it doesn't need to calculate much, but needed more or less to decide where my hand need to land before closing it, and to calculate the proper angles here, which means sending some signal through some hundreds of nerves. So it's not easy, because one could say, okay, so inverse kinematics is so boring, I can stop studying it. Well, probably what we need is something which is conceptually very similar to inverse kinematics. So deciding which actions I need to perform. But if it is even worse, because I needed to do it in a stochastic way, and we are still not very used to this, because the CVs or students usually have a small part dedicated to statistics and in general stochastic processes. And I needed to understand what I have to do here. So it's not that another issue, which is, by the way, not solved, is to understand what happens in the brain. So, because for sure, somewhere in the brain, there is a mechanism to decide what to do here and here, depending on the task. So this is a typical research challenge or idea, right? So, and then I have a musculoskeletal system, this one that I've shown you. This affects the sensory system, because depending on how I move this arm, I will get different. For sure, I see the arm moving, and that's okay. But also, when I land on the object that I want to grasp, I have a sensory feedback, and it is distributed on a surface with here. One of the good things here is that I get a measure of I have a change I have deformation. That deformation gives me an idea, since I have this, it's like having a matrix of deformations, give me an idea what I am grasping, even if my eyes are closed. And then the ecological niche, so the famous three constituents, right? So the agent itself, the tasks to perform, and the environment. In fact, if I had no, this, by the way, I don't know if there are studies about that, but because if I am on the space station and I cannot exploit the gravity, I need to do something different. So, by the way, this could be another, could be a koan, by the way, because just, okay, this, you know that we still have to announce koans. This could be a koan idea, so how to think of a passive, how the passive grasping translates in a non-gravity or low-gravity environment. So there have been attempts, just to say that you may be spend less time, I don't advise you to do that with inverse kinematics, but you may have to study something even weirder. This is an attempt by, actually by Fumiya Ida himself, and if you check in the archive of the lectures, we will find at least one lectures by Fumiya. So actually, the description that he tried was in terms of attractors in the dynamics. Attractors, as you may know, is a typical concept of nonlinear dynamics. They are not exactly stable. Here they are represented in the picture like a deformation in the phase space. So the phase space is the space of the coordinates describing the behavior of a system, like this dog-like structure in the space. No? You know, if you have a mechanical system, you have a number of free coordinates, Lagrange equation typically, but the idea is that you have a set of coordinates that allow you to give a trajectory in this abstract space, which is the space of coordinates. And in this space, non-linear systems have attractors that are area of this space where if they are there, they tend to be captured by these attractors. Now, attractor means something that attracts. There are area of the phase space which attracts. The idea proposed by Fumiya is that basically what happens in the dynamics of this puppy dog is of this puppy fictitious dog is that you exploit the attractors. So you understand what's the problem, no? Because there are models in nonlinear dynamics, but they need to be developed and they need to be applied. And not always they work. So they are not well known as the models, for example, of linear dynamics or the rigid body dynamics. That is the reason why these ideas are still research ideas. So we need to develop the models, we need to apply the model to the new robots, and we need, so there is, my estimate, 10 or to 20 years of research work in front of us. After that, we will have robots comparable to an ant or a spider. So really much closer to the Hollywood imagination of robots. So, and this is about morphological computation. And we have seen that in a simple system like an ant, the interaction with the terrain is a key ingredient of the way the ant works. So interaction. If you remember, we were talking about collective behavior, interaction, evolution, and development. And today we want to go a little more deeper into this concept. So another typical behavior is the swarm behavior. Now, I don't dare to show you a video, but you all have seen a swarm of birds. And what is interesting is that this complex behavior actually comes out by a few simple rules, the most important of which is to keep a distance from your neighbors. So with 2-3 rules, you have this very complex collective behavior of birds. The other concept is orchestration control. What I mean as orchestration control, I mean that I don't control every single function. For example, if I want to control a swarm of robots, not necessarily because you have a small swarm, you can think, if you take the rules of the swarm behavior, so if you put them on 100 robots, small robots, this has been done, for example, years ago by Attilio Martinoli at EPFL, but by many people actually. You can have a swarm behavior of a group of 100 small robots on this desk. How I can orchestrate a swarm of robots behavior? For instance, I can change the speed, or I can change the minimum distance or the range of distances between 2 robots. In this way, with a few messages, I can change radically the way the swarm behaves. Also on this, if you go in the archive, you should be able to find a couple of interesting lectures on this. But the idea is that I don't tell to every single robot of a swarm what it has to do. I just change the parameters like distance between two robots. Then, in this case, I don't control every single joint here, but just a couple of basic information. This is the idea of orchestration control. Something that in part has been applied, in part has to be developed. Then, we have talked about the information self-structuring coming from sensory motor coordination. So actually, in the example of a snake bot that I've shown you, it's enough to put some small, so to give the objective of maximizing the predictive information to the evolutionary algorithms creating the snake to obtain a snake, a snake walk by the very similar to what you have in nature. So, but now we will. I already show you this one, I think, but time perspectives. So, and we have. We have seen how so we have different time scale. And the learning, it's not surprising that the learning is becoming very popular. Learning is basically a way to adapt your strategies to the environment. I may. So if you, I want to show you something.
Fashion is innovation. It's the cutting edge of how we look, how we think, and how we feel. Flashback 1700s. A growing middle class wants intricate.
Okay, I may have shown already this, but it's also always. So this is a typical example. Now this is, here you have swarm behavior. You have morphological computation, because this is not a swarm of similar objects. So it's not a swarm of birds. It's if you want, a hierarchy of different networks of different swarm interacting by exploiting the morphology, and the overall behavior is emergent. And I mean, it's clear how far we are from being able to build something like this, but it's also a source of inspiration. You see, it may take centuries before we are able to rebuild from scratch something like this, but something can be taken, because here I was tempted to show you a swarm of birds, which is quite practical, but this is also a swarm. This is well, a swarm. This is a set of interacting swarms, and the result of this interaction is us. So let's go back to the lecture. So I've shown this because I think it's what I've shown you already, but I want to repeat here is that actually from that cell actually is a human cell. You may have noticed that appeared the word cholesterol, right? So it's because there is a delay problem. And so from that cell, by evolution, you arrive after billions of years, you arrive to us. And we, as I underlined already, we learn to grasp, starting with a very rough, small arm, with a rough, small end, and over many months, we developed together the brain structures and the muscle and the physical structure to grasp. So it's not surprising that we still have a lot of problems to implement the grasping in robot. And third, the third level, that is probably what now we can mimic well thanks to machine learning and deep learning mechanism, is the fine-tuning of our capabilities. So what you get with training. With training, now I mean training to play tennis or soccer or whatever. Now you try and you try again, and you refine your capabilities, no? Because you can be good. So we all are able to grasp something. It's not the same as being able to catch a ball with a glove or to a basketball, right? And to launch it properly. This requires. So they have this level. I would say that the application that today has been done by of deep learning, which is a very promising approach because it's very effective. So it works much better than previous arguments that have been proposed. Is basically deep. What is applied in robotics is deep reinforcement learning, meaning that it is basically reinforcement learning, and so addresses in this schema, it addresses the here and now. So we already know more or less what the system has to do, and the learning system fine-tune the parameters, the many parameters. So this this idea was already actually in the mind of Turing, but Turing, I don't know if you had the opportunity to read, and if you can easily find it on the internet, the famous article where he proposes the Turing machine. He is excited and very optimistic of the future of AI because they were building a 1 megabyte RAM computer. So they had this idea that learning is critical and development is critical in the construction of an intelligent, artificial or natural intelligence was there, but they had was a dream supercomputer in the 40, early 50, had 1 megabyte RAM. So in comparison to the 200 that you have now. No? So and we may still need some more. The Bernstein problem for your is basically the problem was posed by Bernstein, who was a physiologist, which is given that I have a rich flow of data from in a human, no? I have a rich input flow of visual characteristic from the eyes. I have smell, I have touch, I have a number of I have move, no? So I know my position in the space through the limbic system. So I have a continuous flow of data. The Bernstein problem is how a representation of external world arises from this flow of data when it enters into the big networks of neurons that we have in the brain. This is a problem that is still is the holy grail of neuroscience. So how can it happen? And how it could happen? One of the things is this cross-modal association. So putting together learning and data coming from two different things. Because if I see this phone and I try to grasp it and I can't find anything, it means that this is not a phone, but it is an image on a phone. So I need to put together different, we do it all the time. When you also, when you look at someone, you typically see some movement. At some point, the person will talk. So you continuously integrate cross-modal. You do cross-modal association, means that you associate what you hear, what you see, and what we touch, and even what you smell. And we do it in part consciously, but in part unconsciously. So I may realize that in front of me is an hologram because I don't unconsciously feel the smell of a human, but I continuously check. Because you become aware of the smells when they are very strong, but we all the time are sampling the environment. So how this, and we do this cross-modal association. So taking data on the same object coming from the senses together and to see if they match. This is known as sensory fusion or multisensory fusion in robotics, and it's very effective in simplifying the scene recognition. Then we have learning. Big problem of concept formation, I would say it's still unsolved from this perspective, because why we talk about concept formation? Because one thing is to write a program like the Tower of Hanoi program, knowing the programmer, that there are blocks and that there are different color of blocks, and that you can put one on the other and you can program this. Another thing is your system, Bernstein problems applied to robotics, getting a constant flow of data and abstracting that this is a black block in front of me. And then understand that it is a phone that requires a lot of information that we have, because we are continuously interacting with other people, reading on books or on the internet and watching television. Because for me, this is a piece. It's another piece, 100 grams more or less, can be thrown, used as a weapon. Because we used to laugh when typical wild people living in the bushes. But this is if I have no other information, this is good to keep paper still, or really to hit someone if or as a number, right? So if you don't know, so we have seen this idea, and we can go back on this. Is this extraction of mutual information? So something that I can abstract if I have a flow of data is that if they are somehow connected with each other. This can be done by measuring characteristic of this time series, because finally you have a number. Now, if you think to what happens to your eyes, now think that you only have one for simplicity. You have low, if you want a low definition, you have 1000 by 1000 pixel colored coming every 30 times per minute. Now, and this gives you a number of you have a number of instantaneous partially overlap then, no? And from that you need to understand that there is something outside. What you can for sure you see from these measures on these numbers, like mutual information. So you see if two streams, left eye and right eye, are connected, is, for example, seen by mutual information. Then you have a prediction. Some way you know already what's happening. Now, if you see this hand moving, you predict that it will follow a certain, and then the categorization. You know. So because the idea is that from sensory motor coordinated interaction, so I move this hand and I see, because consider also this, because we are not conscious of these things that we do, but if I move this hand in this way, I predict that it will do what I want, because I have cabled here that when I move certain muscles, this happens. And then I have the feedback, because here I feel the weight distribution, because I get back in an approximated representation of the load on the arm. I see it. This is the cross-modal integration. I see it, and the measure that I get on the position of the arm and what I see match. Match how? Not as precisely as in an industrial robot arm. More or less, this position matches with the load distribution that I feel and the kind of order that I gave. Again, it would be interesting to understand in which precise areas of the brain this information is processed. Could be a big achievement. So this is our problem, is how to abstract the patterns, while the corresponding problem of the frame of reference of a symbolic approach is that shown by the Simons ant on the beach. So if I change the context, all my logic of behavior collapse, and I need to. And this is in favor of the necessity of having, call it, an emergent set of behavior or a self-organization of behavior. Because since the world outside changes all the time, and many times these changes are unexpected, so we continuously, even Murphy tell us that whatever you foresee, something different will happen. Many times it is positive, other times it's negative, but of course it is positive or negative depending on what we want to do, but it is basically unexpected. So the real problem that you need to manage with in an intelligent system, whether the agent, a physical, intelligent, physically embedded thing doing things that we call intelligence. You remember that we don't have still clear ideas of intelligence. We believe, but we have many definitions. But this is the symbolic approach collapses because you may always find something that is not foreseen by your frame of reference that you, the designer, put in the system. This approach of abstracting the general concept from the interaction and the development is something that is so it's something on which researchers are working. And yeah, I think it's very interesting to talk about the lack of Nunez hypothesis, which is, by the way, which was proposed in this book now, the year 2000, where mathematics come from. Because the main idea that is described there, and that was later proven, also you can find a guest lecture by Rafael Nunez, both were at Stanford in those times, about this topic, because after the book, there are now evidences that what they say is actually probably true. So mathematics is the most abstract, probably the most abstract and thus part of our representation of the world. So you may think that mathematics is something. So there have been also philosophers like Plato saying that mathematics stays in a separate world from ours and is completely untouched. So it's something completely different. We can understand mathematics, but as limited beings, we cannot. What they have shown, and so they propose arguments, and this has been shown also with imaging, with brain imaging, is that when a mathematician, for example, demonstrates the limit of a function, and for instance, think to the example is the limit to infinite. Initially, you have many movies. Check this guest lecture, you will find them. Many movies where you see that the mathematician, while writing on the blackboard the limit, actually mimic the movement like it was going really to infinite, so having a very long way out. And what is even more interesting is that if you look in the brain, the motion, the working, the areas that in the brain are in charge of locomotion are activated. So actually, in his the body of a mathematician performing a limit to infinite behaves like so the brain structures are activated like it was really walking and really thinking of a very long walk. This is and this is mathematics. So the very nice idea that I would consider very also at least partially verified, that at least some ideas of mathematics are really embodied in the sense that a limit to infinite is going very far. The thesis is that actually we have invented mathematics by abstracting things that we already do. So a limit is an abstraction of the concept of movement. And so if I move to 0, I move I tend to go in a very small place. If I move to infinite, I walk. And then if you think you may also, I also suggest you to have a look to the book, because so the main idea is that the principle of motions that we have in our body are the basis of mathematics. If you think about now, the space representation, for example, comes from a concept of proximity, and so it's really very suggestive. I said news about that is that you know that on the Voyager they have put some mathematical formulas with the idea that aliens catching the probe could actually understand us, but this idea that even mathematics come from your body structure means that it depends. If the aliens are humanoids, they will probably understand our maths. Otherwise, I don't know, they have to be much more advanced than we are. So but this is quite a strong thing to know. No? So also our physics is more or less developed on the basis of how we are shaped. I quoted already these approaches that you can find plenty of information on this. Artificial neural networks, which are simulation of a neuron, of a neuron net. Deep learning, that I would say, if I really can put it very low level way, is a neural network with many neurons and many layers. Where many neurons means 100,000 and many lawyers means hundreds of lawyers. Of course, you have, but what I think is extremely interesting, that by adding more entities in your structure, the good odd neural network which work well, in many cases, it becomes much more powerful. As told, what we apply in robotics is typical using deep learning for reinforcement learning. This is what has been done so far. Then other approach is information theory, because it is useful to give numbers too, because you say, you know, so the two examples are the fully actuated worker and the passive worker. I know that the passive worker can have a 1,000 line code to be controlled. Why? A serious humanoid can easily have 100,000 lines of code. So I know more or less. So I could say that the measure of information managed by the passive structure of a Bible worker is about 100,000 line of codes, because I neglect the 1,000 line of code. I say practically zero code in comparison. And so this is a very rough way of saying it when you already have built both systems. But how to do it in advance? I need to have a method to give it, to say how much information is managed in this dynamical behavior. Information theory, starting from Shannon, allows to do that. Network physics is another important tool, because it's, if you want, an advanced way to manage. It's science, network science, is science about networks. So how many objects can be connected between them and exhibit some nice behavior. Then integration of timescales. I probably have shown this quickly, but I want to go a bit deeper into this, because if the timescale here is it's below is in log seconds, and above is in seconds, then month, then day, month. You see that you have really a coordination of different time scale, because on the millisecond scale, you have the spike of the neurons. Then if you move a bit still below 1 second, so in the hundred of milliseconds, you buffer the data, for example, the visual data coming from your sense, for example, the eyes, and you you understand the situation. You know that typically a human can brake in hundreds of a car in hundreds of milliseconds. So this is the scale of small reaction. Then we have phenomena which are linked to, are on the seconds or minutes scales. For example, emotions. For example, movement, muscular, and this is for humans. Another interesting thing is that this could be done for every animal species. I give you the question and maybe someone will answer next time. So because this could also be done with plants. Also plants react to the environment. If you look to a plant that you have in your house, for example, and you move it with respect to the windows, you will see that it will slowly move in and out. So plant moves, they just move much slower than we do. And then we have, and this is the scale of everyday life of a person who is in a specific stage of development. But then we have 20 months that are needed to learn to walk. You have more or less the 24 months, 3 years that you need to start to talk a bit. And you have 20 years that needs to become an adult, and then you have 25 years to have a full and final brain structure. So you should start still more if you are less than 25, because you can still enlarge your brain structure. Then it will only be connections, like me. So I can only add a connection, and I'm happy because thanks to age, I have more free spaces because neurons die, so I can put more connection there. So study when you are young, so you will have a big brain. But in part, this is probably true. And then we have mechanisms which are a bit. Yeah, thank you. Like natural language, and this will be a topic for another example. Some rules. Applied. From the origins of scaling structure in cities. And then, okay, I stop here because I noticed that I am about 15 minutes. There are many things that we can tell. As told, the purpose of this lecture is to seed some curiosity about these problems, about the solution that have been proposed, and to trigger your also your self-study. And the purpose of the koans that will be announced this week is to even give you a concrete goal to foster your attempts. And so thank you for listening. I think that I took too much time, so please, if you have questions, raise them after the guest lecture. And now I am very happy to welcome Martin Sterlen from the University of Plymouth. He will give a talk on how actually this theory can be put in practice, in particularly looking at co-development of brain and actuation and morphological computation. Martin, welcome. Thank you for accepting the invitation.
Thank you, Fabio. I'm happy to be here.
The floor is yours.
Okay, thank you very much. So I'm gonna.
If you are still there.
Yes. Let's see. There we go.
Yeah,
okay.
I think.
Can I do that? Can you see that? Okay.
It's muted.
Fabio, can you see that? Okay. Let's see.
Martin?
Yeah, can you hear me?
He is now the presenter, so.
Can you hear me now?
Martin?
Yeah, can you hear me?
What's happening?
Okay, can anyone else hear me?
It's talking already?
Yeah.
Okay, Fabio, can you hear me at all? Or can anyone? Okay, I can see a chat message here. Oh, the audio is okay. Okay, so it sounds like people can hear me. Okay, cool. Looks like Fabio can't hear me. That's right. Can you guys see as well the presentation slides? Okay. Okay. So I'm just going to go ahead and I'm going to assume people are hearing me. Okay, yeah, so first of all, I'd like to thank Fabio for letting me present this year. Really happy to be here. This Shanghai Lectures was a important part of my education, can we say. I kind of participated during my studies, my PhD, and also helped organize a bit in the past. So I'm really happy to be here and to present some of the work that I've been doing in the last couple of years. And that is, you can say it's largely inspired from this lecture series. Okay, so I'm hearing some people's talk. Maybe you want to mute your microphones. Make sure you mute your microphones, guys. Okay, thank you. Right, so I'm just going to keep going. So the talk is basically on co-exploring brain and body in the field, and hopefully this will connect somehow with the rest of the topics in Shanghai Lectures, and also we will understand a bit more about this title as we go along. So I was working after my PhD, and also partially during my PhD, on things. I think I'm hearing someone, so could you make sure you mute your microphones, please? Okay, so I was working on basically approaches for learning in robots, taking some inspiration from development in humans, and trying to see if we could, what happens if you have a robot and you want to try to teach it something almost from scratch. So in a sense, emulating some the way we come out, a bit as blank sheets of paper, and go through some developmental stages. How can we do that in a robot? While doing that, I quickly ran into problems with the robot breaking itself. So if you have a robot with, in a sense, a developing mind, so the robot starting from almost blank sheets of paper, then you can imagine that this robot will make mistakes, just like we do as we grow up. And so this idea that if you have a developing mind, you require also quite a robust body kind of stuck in my head. And we realized that we probably need to build a platform, because there really was no platforms on the market that could enable us to be soft when we wanted to be robust, and then be precise enough when that was needed. And this led to a project called the GummiArm, which I'll introduce a little bit first, and then we'll go into how this relates to the field later. Now, this is a video, just let me know if you can't see the video, but it should be all right. Just showcases this arm a few years ago. So just shows that you can have it quite low stiffness, so it can be kind of soft, but you can also stiffen it up quite a lot, so it has a stiffer behavior. And when it is stiff, it's easier to do things that require precision, so traditional robot tasks. So this is just, picking up something, placing it somewhere accurately. By the way, this is teleoperated, so it's not actually doing this autonomously here, but it's just showcasing the properties of the arm itself. When you're soft, one of the cool things in my mind is that things like interacting with the physical world becomes a lot easier. And this is really important, right? Because most robots we have today, they draw their links back to industrial robots, which operate in very controlled environments. Outside of those environments, we will need to interact physically with the real world. If you have a soft robot like this and you want to open a drawer, you can simply put the robot in a soft configuration and put the finger behind the handle in this case and pull backwards, and everything kind of falls into place. So the idea is that there's less control required to actually perform that kind of physical interaction. We'll get back to that a bit later as well. This is how the arm looks in a diagram, or from a kinematics point of view. You can see it's more or less scaled in size to an average female arm. It has 7 degrees of freedom plus the end effector, and there is a range. You can see there's a lot more actuators on here than those 7 degrees of freedom, and that's because it has an antagonist setup, and I'll get back to that also a bit later. And the servos are commercial ones, so it's commercial servos. All these green parts are actually 3D printable, so it's a 3D printable robot. And if you wanted to build one yourself, it's about £4,000 to £5,000, or maybe $5,000. So the idea was, okay, if we are going to build a robot platform that can be used for, say, developmental learning in robots, it will probably still break itself at some point. And so we wanted to keep this robot both open source and easily replicable, so that we could have a range of these robots around the world, potentially, all collaborating and together improving the design. So the arm itself is on GitHub. You can download the code from there. You can also download the 3D printable pieces from there. And the idea is you can have an open source robot, but it only really becomes replicable once you're also able to easily manufacture it yourself or in the lab. So this robot can be 3D printed on standard 3D printers. And so this idea of that Fabio has been working on many years as well, this idea of replicable robotics. So how can we make robots, the development of robots and the testing of robots adhere more to the scientific method? And by making robots replicable, we can also move towards replicable robot experiments and a more scientific approach to robotics potentially. So if you want to build it, we also need to make sure we have instructions for how to assemble it, how to run it, etc. So we have this kind of IKEA-style build instructions you can follow. And all of this leads to an interesting cycle of development, I think, which looks something like this. So imagine you start in the lower right-hand corner, you do some crazy experiment with your robot, and you crash it into something, or the robot, the robot is learning, so it makes a mistake and it breaks apart on the robot. So if we go now in the clockwise direction, you can see the broken part there. So we want to fix that. We open up the CAD model from the GitHub site. We not only print it out, but first we improve the part of it. We make it make some structural adjustments, improvements to the part, make it more robust. Then we print it out, put it back on the robot. Now the interesting part is that process now only takes minutes or potentially hours. Okay, so by the time you've done that, you could have also had improved upon the algorithm to help you prevent those kind of accidents in the future. Test that code, refactor it, and put it back into the robot experiment. So by the time you have about the same amount of time as your hardware is improving, is evolving, your code as well. So you can do the two at the same time. So a type of concurrent engineering here. Of course, Fabio has gone into this in depth. His idea of these three levels of adaptation, where our behavior in the here and now emerges from the ontogenetic and phylogenetic levels. This also means that if you look at something like evolution, evolution has not just taken a body and then optimized that, made a stiff body, optimized as much as it could do, and then put a brain into it and optimized that as much as it could do. That would be a more typical robotics approach, traditional one. The idea in evolution is that you can do both at the same time. And so if you have these type of 3D printable robots, replicable robots, you can potentially do the same thing and come up with more optimal solutions. And that then leads to more interesting developmental approaches and also here and now type approaches. This also links back to the agent design principles Fabio's gone into. Again, this is from the book, the famous book. And if you think about this, this really relates to this design principle of the complete agent. So the complete agent must be taken into account in design, not only the isolated components. So we need to, when we design our complete agent, we should try to think about the brain and the body, the hardware and the software at the same time. And this is what we're really trying to do here. A bit more into the ARM design itself. So it's based on these agonist-antagonist joints. So you might know that a lot of your joints in your body is based on this. Actually, the idea of agonist-antagonist muscles is a bit of a simplification. In most of your joints, you have more than two muscles spanning that joint. Often they span multiple joints. But the simple idea is that you have this biceps, for example, acting against this triceps, for example, in your elbow joint. That means that you can move the joint by moving them differentially, or you can pull on both of them, co-contract them, and then you stiffen up the joint, right? We can become stiff when we want to, or we can be soft and floppy when we need to be. In the GumiARM, this is replicated through some composite tendons, okay? These composite tendons are activated by some pulley wheels, and these pulley wheels are driven by digital dynamical servos. Now, the important part there, if you want this to be able to be a variable stiffness joint, is that these tendons, these springs in a sense, should have a certain nonlinear property, something akin to a quadratic spring. And you can see that if we use a rubbery Filoflex element in the middle, if you just have the rubbery Filoflex element, you can see that as you start elongating the tendon, that's the green line in the graph, it resists a bit in the beginning, there's a bit of load, but then it just really starts stretching up to 10 times its length. And by adding this stiff or non-elastic nylon line around it, As we start pulling on this composite tendon, you can see it starts resisting more and more and more, and we get this close to quadratic or exponential relationship, which is what we're looking for. And what's happening there is that a non-elastic nylon line straightens out more and more and takes more and more of the loading. Now this is key, because this is also reflects the combined elasticity of our muscles and tendons, and this means that if both of the muscles or combined muscle tendon systems on each side of the joint has this non-linear quadratic property, then you can control both stiffness and position of the joint. If it was just linear springs, you could only control that position. Right. This enables us to be quite robust as well when we're in a soft configuration. You can see that this arm can absorb quite a lot of energy. That's a 2 kilogram weight. And if you did that to your arm would probably have quite a similar behavior. So even though it's 3D printed, and you might know that 3D printed pieces are not necessarily all that robust, especially this was a PLA version of the arm. Since we have these elastic elements everywhere, this softness, we can absorb that energy and prevent any of these stiffer pieces from breaking, similar to your bones. You have these elastic elements that are able to absorb the energy. You can then, of course, vary, as I said, the stiffness through co-contraction. Now, stiffness, you would think typically for stiffness for a joint, you would measure by, holding the joint passively at a certain pose, then applying some kind of torque, so maybe putting a weight on it, and then measuring how much passive deflection you get. Okay, so that's what we're showing on this plot. You can see that if you have 0% co-contraction, this is for the elbow joint, that's the blue line, and you apply a 2 Newton-meter torque, you get something like 45-50 degrees of deflection. If you then start co-contracting, that's up to 100%, that's the black line. For 2 Newton-meters, you'll get something like 15 degrees of deflection. So you can vary that stiffness quite a lot, that passive compliance in the joint. By the way, just to say that this is certainly not the only way to achieve variable stiffness actuators. This is a field in itself. But there is a range of interesting properties of this type of variable stiffness actuation I can get back to later if you have questions. Since we have using rubbery element instead of just metal springs, you can see that if you have a low amount of co-contraction, there is quite a lot of oscillations, but they do die out reasonably quickly. And as you co-contract more and more, here we're releasing a 1 kilogram mass from the end effector. You can see the right video, there's not that much oscillations actually. So they die out at least quite quickly. So you can exploit this viscoelasticity of the rubbery tendons to dampen the behavior of the arm, which is nice. And then what can you use this for? Practically, as I said, interacting with physical objects, with the real world becomes quite a lot easier. Here I've put the arm to be quite soft, and when I'm soft, as I've seen before, we can easily interact with things like cabinets, opening them, without having to calculate exactly how that cabinet moves. I can then stiffen up, and now I have a stiff finger, so I can push that door open. A lot of robots have fingers that are only able to contract, not able to stiffen up. You wouldn't be able to do that. And then I can soften it up again to open the other door. You can see that when I pull backwards and open this door, I really don't have to do much control. I just let the joints be soft and they fall into place as the door opens. So these kind of tasks could potentially be a lot simpler to do for robots if you have this ability to vary your stiffness, vary your passive compliance. As humans, we are also using co-contraction in other ways. There is evidence that we use it to stabilize our movements. So if you look at, this is a paper from Journal of Neurophysiology. If you look at this experiment, this figure, this human as an overhead view of the human, and it's supposed to do this kind of center out movement, so move from that central dot out to either 1, 2, 3, or 4. Now those dots can be of different sizes. You can imagine trying to aim for one of those targets at 45 or 30 or 5 millimeters. And what we can show that as we aim towards smaller targets, we actually increase the amount of co-contraction in our muscles to be able to achieve that, okay, to reduce the oscillations. And the plots you see, the top one, that's just showing the different muscles that they were recording EMG signals from. So you can see the biceps 1, biceps 2, triceps 1, triceps 2. That's because the triceps, biceps and tricep muscle are actually multiple units. But you can see that as you go from 45 to 5 millimeters, so 45 are the black lines, columns, 5 millimeter are the white columns, you can see that you start using your muscles more for 5 millimeter, right? And you do that both in the biceps and in the triceps, for example, which means you're actually co-contracting more, right? So we use this ability to, even though we're pulling on these rubbery tendons, if we want to move quickly and stop without oscillations, we can use co-contraction dynamically during movement, okay? So we can vary it through the movement. This is also something we can do in this arm. So just a quick example here, as we're moving the shoulder up, you can see that the bottom pulley there stopped before the top one. And you'll see the reverse happening when we move down, because that was in slow motion. This is in real time. We'll see it one more time. So you'll see the bottom pulley will stop before the top one. That means that as we're pulling on the top one, we're increasingly also increasing the co-contraction towards the end of movement. That means we can stop with very little oscillations at the end. Yeah. So we can exploit that, and that gives us a good response to, say, a step input, even when we're starting loose. So if you have just traditional feedback control, and you imagine you have 0% co-contraction, that's the blue line, you're basically pulling on 2 rubbery bands, right? So it's quite hard to do that precisely. If you increase that so you have a stiffer robot, then you can have a better response. But often we want to move with a low amount of co-contraction, low amount of stiffness, because that's when we really can absorb impacts, right? So if I'm moving quickly, I want to be able to, if I calculated something wrong and I hit something, I want to be able to absorb that impact. And with this type of approach, where we increase the co-contraction during the movement, we can see that even if we start from a loose configuration with low co-contraction, we can still have a nice, tidy response to that step input. Now, this project, as I said, was started to be a bit of a community effort, and we've started seeing some big movements in that direction in the last year. So there's about 5 or 6 groups now around the world building these arms or related technology. One of the projects that has shown outputs already is the Gumi ankle, and this is a group in Colombia that basically took the same actuator design, improved their bit, and as using it for a ankle exoskeleton to help people that are problem controlling their ankle movements. So it's a variable stiffness design again with the same type of tendons. And then we have the first fully operational clone of the Gumi arm has been built in Australia. That was this month at the Australian Centre for Robotic Vision, Queensland. And so we're working with them to see what next steps we can collaborate on to develop the project further. Right. Now we're going to take a little bit of a change of direction here. So I'm just showing you. I was talking about the industrial environment before. The factory robot in a closed cell, working almost without sensors, and then we want to put robots into the real world. Really, that's what our aim is now. And this is to me one of the most interesting places to put them. So into the field, okay? So this is I think it's a broccoli field here locally in Cornwall, in England. And the interesting observation is that if you look at the crops that are sold fresh in your supermarkets today, so you think about soft berries, a lot of vegetables, etc., they are still harvested by hand. And the reason for that is that you can have, so you can have harvesting system for a lot of crops, including grapes and some berries, but these harvesting systems are not very clever. They are basically either beating the bush or blowing on them or doing some kind of, they're not very precise. And so there will be typically be damage to the crop. And so most things that need to be sold without blemishes are still harvested by hand around the world. So there's a big potential here. If you haven't seen broccoli harvesting, this is how it happens. You basically have human pickers walking in front of this moving platform, this tractor, quickly cutting, picking up, trimming off the leaves and putting them onto these conveyor belt that goes into a sorting facility in the back of the tractor. Okay, so quite intensive work, and you can imagine this happening during all kinds of weather conditions. This is a picture from California. So this, I think, is leeks being harvested. Again, there's not a lot of appetite for doing this kind of work anymore. So it's also starting to get difficult to attract people to do this job, and that's true all over the world these days. So that's another push for actually trying to automate these things. This is raspberry harvesting. You can see here it's inside a plastic tunnel. That's another interesting environment. And then you can also have greenhouses. Now, for the pickers for these kind of crops, the manual harvesting often represents up to 50% of their overall costs, which means that there's a significant amount of money to be saved if you could automate some of this. So I think, at least, that we need soft and precise robots in the field. You need robots that are soft because they should be able to absorb impacts, make mistakes, etc. But they should also be precise enough to pick, say, a raspberry or a strawberry without causing blemishes. One of the things that characterize the agricultural environment is that your sensory data will be very noisy. You can have all kinds of weather conditions. You can have rain, you can have fog, you can have wind, even just direct sunlight. That's actually one of the biggest problems you will face because it's so variable. Our human eyes are very good at actually overcoming variations in light, but it's a bigger problem when you're doing computer vision algorithms, etc. The sensory data can also be very ambiguous. This is a picture of sugar snap peas. That's these green bellows in front of their green stems, their green leaves, etc. So if you want to do some kind of thresholding here on color, good luck. It's not easy task. So you might also have to be a bit more adventurous in what type of sensing you use and in what types, for example, which part of the spectrum you look. Given that we have noisy sensory data, complex environment, errors will be made, I believe, and that's where this links back to the developmental learning we talked about before. And so compliance is needed, I think. You will have collisions with obstacles, which is very hard to prevent if you imagine a system operating for thousands of hours by itself. There could be wooden poles, there could be other hard obstacles. Of course, you're working often alongside humans. You might not be able to automate everything straight away. So you might have to think about what injury can this robot cause a person if it doesn't calculate things properly. There could be cutting mechanisms, etc. And then, of course, it could entangle itself in cords and branches and stems, etc. So if you go back to our agent design principles, I think this is what Fabio mentioned earlier as well. This links back to the three constituents. So we need to take into account not only the agent, but also what tasks should it do. So in this case, what crops should it be operating on? Should it be harvesting them? Should it be spraying? Should it be weeding? And also the ecological niche. So we need to make robots that fit into this niche, in this case, in the field. And we need to take into account this noisy sensory data, etc., when designing the complete agent. Oops. Okay, I'm just going to warn you, there's going to be a very loud video here, so you might want to turn on your volume a little bit. And this is just going to showcase a project that we ran this summer, just completed this summer, where we showcased tomato harvesting in Shanghai, China. And this was a collaboration with Shanghai Jiatong, the School of Agricultural Sciences, and Sungqiao. So I'll just show you a video showcasing one of these projects that we're running towards agriculture, putting these robots that we can that can quickly be prototyped into a real agriculture environment. Okay, I'll leave it there. So basically, this is a design that has soft fingers that are able to adapt to the tomatoes, etc. The main point is that this is, again, built onto the technology we saw before. So it's just an extension of that. We're putting a robot into the field with variable stiffness properties. And again, we were able to do this in something like 4 months. We started with a robot that had never picked any tomatoes for. In 4 months, we're able to do this kind of concurrent engineering with the co-exploring this body and brain at the same time and coming up with a solution for a real application in the field. This is pushed further by a spin-out company that we set up, and we're aiming towards building complete platforms that can operate in the field with this type of technology. That's all from me. So hopefully that made sense. And if there are any questions from anyone in the audience, I'm happy to take them. All right, cool. So can you hear me, Fabio? Yeah.
Yes, yes. Okay. Thank you for a very nice talk. Thank you.
Okay, thank you.
Also very fit to the purpose.
Okay.
Thank you. So, as Martin said, please, if you have questions, raise them. Maybe it's useful if you also send a chat so we can see if you.
That's as easy. Yeah. Feel free to write them down.
Hello, good morning from Spain.
If you wave the hands, we don't see.
Can you hear me?
Yes.
Okay, I have a question about the autonomy of the harvest robots. I want to know how much time does the battery takes to rounds off.
Okay, yeah, it's a great question. So the arm you saw picking right there was one picking tomatoes. That was just, it was not actually connected to batteries, it was just running off the mains. For the last, so this kind of platform where we're looking at picking the soft fruit You can see there's 4 arms on there, and then there's a rigid refrigeration unit as well. For these systems, we're basically trying to target 24-hour operation. But of course you will need to swap, you will either need to charge your batteries or swap out batteries. The current idea, this is very early stage, is to try to have batteries that last for about 8 to 10 hours, and then you swap them out manually. So basically lift out the battery, put in a new one, and plug it in and keep going. So the key point is really to try to enable 24-hour operation. Anything else? Did I answer your question, sorry?
Yes, that was my question.
Oh, I think I lost you. I'll try to type it. Okay, so I lost contact.
Oh,
okay, I can hear you now, Fabio.
Yeah. So if there are no questions, please, this is your last minute for raising a question from the chat or any other tool.
Yes.
So I believe there are no questions.
Okay.
So thank you so much for this, I think, very, very good talk, and for accepting our invitation, Martin.
Thank you. Yeah.
And thank you all for attending today's lecture. Of course, see you next week. During this week, we will announce the koans from this year, which is a good challenge for you students, and we will try to, as usual, they are very interesting, maybe a bit, we give you pain, but you don't have real learning without something. And so thank you all, and see you next week for yet another exciting lecture. Okay. Bye everybody. Bye bye.
Bye bye.